Okay, so pre-lecture 6 is due today. Pre-lecture 7 is due on Thursday, along with project 1. I'm getting a lot of questions about it, so that's a good sign that people are actually doing it. It's not extremely difficult, but it's just more like getting used to the technology project. What we will do is once you build the 2x2 array, make sure you use the symbol for the M bit and don't put 4 1T, 1Cs in the schematic because that it would be clumsy. The next project's due Thursday, March 4th, and you'll start with your array 2x2 and you'll add the equilibration circuit in and you'll add some voltage sources and some pulse sources and you'll actually simulate it. A week from today, the next homework's due, and this is all the projects and homeworks on this list are already posted to BB Learn. What?
A week from Thursday, the homework Tuesday?
Mm-hmm.
So a week from today.
Week from Thursday. Ben is right. We're having an IEEE movie night on Monday, February 15th at 5:30 p.m. You can either come in and we'll take over one of the classrooms and spread out and have like owned individual plates that you can pour out popcorn on, or you can view it through Zoom. This is a special movie. Ben dug this up for me. And it took a lot of work to find this one. Some old comic books from my childhood.
It's a new movie that's come out like about 2 years ago.
Mm-hmm. Yep. Okay, so we're going to continue on with the fundamentals high-speed topics. Basically, it's kind of a top-level look at how we decide which architecture we're going to use. So a lot of that stuff. Yes, we're still behind, we're exactly a day behind now. The project is due, Thursday, February 4th. We're only a day behind, that's wrong. It's Tuesday. Yeah, we're a day behind. Try to keep the names the same as they are on the assignment. I will get over that eventually, but I may dock you a point, especially if it gets hard to find because the name is wrong. The rubrics are on BB Learn. So I literally go through the checklist and check off, did you do this part, did you do that part, etc. Okay, we want to compare the 3 different types of architecture, open, folded, and bi-level. Turns out bi-level is going to require another metal layer. That's not really a big deal anymore, but back in the day, it still can. It adds to the cost of your processing for every metal layer you put in. We're going to look at delay and power. We're going to do a bunch of calculations, and I'm going to have a big chart by the end of this. So I'm going to need, I can't do this on the whiteboard anymore. So I'm going to need to open this thingy up. 93. Okay, and let's get this going. I actually wrote a new slide today. I did not write a new slide all of last semester because I didn't have any time. Okay. Okay, so we've got a 256 megabit DRAM. 256 meg is 2 to the 28th. That's on my little cheat sheet chart, but I knew that one. 2 to the 28th. We're breaking it up into 32 megabit blocks for yield and to keep our row lines short and to keep our column lines shorter. So 32 meg is 2, 4, 8, 16, 32, 2 to the 25th. That's a 5 or 10. If you want to figure out how many blocks we need, we take 2 to the 28th, we divide it by 2 to the 25th, and that is 2 to the 3rd, which is 8. So I need 8 blocks. All memory is divided into different blocks to keep the row lines short, keep the column lines short. and to keep the yield up. Okay, this is the slide I wrote today. Wanted to talk about row decoding. There's a couple of different ways we can do this. We can go through like our, let's say we have 10 bits of row address. I could take and do my 280, my 110 thing, sorry. I have 9 to 0 coming in here, and I decode it to 1023 to 0 on the output, and then I take each one of those lines and, no, this is global. So this is a global decode. I'm going to run each one of those wires to the pitch on the array. So now I only have to, I can put this block someplace else. And I still have to build it, and it's still going to take up space in the chip, but I put it away from the rows, and then each row gets one of those lines running to it. It's kind of a routing nightmare when you think about it, because I've got 1024 lines and I've got to get them all to the rows. But it's not really all that bad. This is going to be the most compact at the array, because I only have to run one line over there.
Kind of slow because it's separate from all the rows.
Yeah, you need to have a big buffer on each of those 1024 outputs in order to drive the resistance and the capacitance of the line. You're probably running it metal at least, but it may be a centimeter or so. You have to take that into account too. Now, I could do a local row decode. And a local row decode, I take each word line 0, word line 1, I would have to run all 10 bits over there, and I'd have to put in a 10 input AND gate, maybe with some inverters in there, right next to each of those word lines. Now I've got to run 10 wires to the word line. They're going to fit, they've got to fit in that word line pitch. So I either need a whole bunch of layers of metal to get this going, and even that doesn't, because you have to have vias to go in between them and all this, it's a pain. This is going to give you, this is local. It takes up a lot of metal layers to fit in the pitch, that's what I said. But then I don't have to have this big decoder elsewhere, and I don't have to worry about driving these lines all the way to the array. Now there's a compromise between these two, and we'll go through this in gory details in some of the homeworks. Okay, it's called hierarchical, and I'm just going to abbreviate it. If I do a hierarchical row decode, basically, I had a picture of it in here. No, that didn't help. This is 03. Where did I put it? I don't know where I put it. Doesn't matter. I drew a sketch of it earlier today. So maybe what I'm doing here is I do this little decoder in here, and it takes in bits 9 through 0, and what it spits out is 4 lines that is 9, 8. So if 9, 8 is 0, we'll just call this, we'll make this a bus, 3 to 0. So 9, 8's going from 3 to 0. There's 4 lines coming out there. And then I have another set of lines, which is 7 to 0. I've reduced the number of lines that I have to run to all the cells by 1. So this just goes, 0 would go to a quarter of the array, of the array, 1 would go to a quarter of the array, 2 would go to a quarter of the array, etc. And we can keep on doing this in levels to reduce the number of lines that I'm running out to the array to whatever I need to be. So I just keep on, I could decode 3 bits. I could do 987, or I could do 98 0.76, etc. This is the terminology they use too. It took me a while to get that. What is column 98 and why is it so important? Okay. So we're going to be using these terms when we're comparing the sizes of the different architectures as we go through here. So this is the open digit line. This was the first generation. To actually do this, if you look at this, I have a sense amp on every single row. I have to fit the sense amp into the row pitch. And it's nearly impossible to do this. If I could set this up so that I could just put one sense amp every other row, then that's called double pitch. I'm putting it every other row. I'm going to need at least a third metal layer to do it. Every time I add a metal layer to my process, it increases the amount of time it takes to build those chips, and it also increases the cost of it. So we ideally want to get to double pitch because that's the only way I can route it. Okay, and this says it has dummy arrays in it. Okay. These have dummy arrays. Not only are there dummy rows and dummy columns, but it turns out the arrays on the edge aren't quite as good as the ones in the middle. So we're gonna put dummy arrays there also. Still, this is, and the way I'm getting around the single pitch problem is I'm taking this digit line and running it through 2 rows. Okay. And then that way I can put a sense amp every other row. I've effectively made the digit line longer doing that. So I have to keep that in mind when I'm building my arrays. Now for a global row decode, this is where we decode in a block somewhere out away from the array and just run the single enable lines on there. They go through, they've got all these things in here that are going to determine the area of the array. How many sense amp strips am I going to have to put on there? What is the width of the sense amp strips? And we kind of went through the calculations for this yesterday. How many global decode strips I have? I just have one coming in. I've got the height of the global decode strip, the number of stitch regions. These are extra regions I put in to make sure everything, I can do all my routing and everything. What the height of those are, the number of digit lines, number of word lines, the height of the block. I go through and I calculate the height, the width of the block. I come up with 29.944350 micrometers squared. Yeah, it's a huge number of significant digits. And the reason why is the guy who's actually doing the layout of the chip, who's packing this block next to the next block, needs exact measurements, even down to that level, because he's putting little micrometer things in there. So we're going to stick this one on bamboo paper. So we've got open. How many possibilities do we have? We have folded. And we have, whatchamacallit, bi-level plaid. Bi-level. And we have different types of row decoding that are going to affect this too. We have global. We have local. And we have hierarchical. I want to see how these things all kind of play together, and why the way engineers make decisions too is kind of like the point of all this. This was, we'll call this 29.9 million micrometers squared. And was that right? Am I right? Open global. 29.9 million micrometers squared. Okay. What?
What a number.
I just make this up as I go along. So then we look at the case if I do a hierarchical road to code. Now, in the global road to code, I only had to bring one line over, and there's no decode at the road. And the hierarchical, I may be bringing 3 or 4 or 5 lines over. I'm going to have to do a smaller amount of decoding there. How does that affect that? What was the change in here? The height of the global strips gets a little bit smaller. But then there's this extra thing in here, these things right here, the hierarchical decode strips, a little bit of extra stuff, not quite as good. So it's 30, and I go through and I do the calculations and I come up with 32.4 mega, and that was hierarchical. We'll know that these are all in micrometers squared. So adds a significant amount of area to the array, but I've got to put that block someplace else. That may be another trade-off too. Okay. That's as far as we got. So for the folded digit line, I don't have to go through the trick where I make the digit line 2 rows long. What I'm doing here is I'm sticking the sense amp for this row, for this pair of rows is right there. And then I put the sense amp for the next pair of rows over here. So now I've got potentially a 4-row pitch that I can put the sense amp in. Wow, I may not need that extra whatchamacallit, layer of metal at that point. So I've just made it a little bit better. The row decode's going to go in this direction. Okay. For the folded, remember we were limited to a time constant of 4 nanoseconds. So that's going to limit my word line length for this architecture to 512. I'm still using the same process, so there's still 12 ohms per square. The capacitance is the same, 0.5 femtofarads per cell, and the RC is where I'm getting the time constant from. The RC time constant will equal n squared times RC for each one of those. So I'm limited to 512 word lines. I think that's a little bit bigger than what we had yesterday. I can put a 256 core in here instead of a 128 core. So I'm getting a little bit denser on there. I still have the area of the sense amps that I have to squeeze in between these subarrays, in between the cores. I need to squeeze the row decode in between the area of these cores. And this is total here. If I have 256K and it's in a 32 megabit block, I'm going to have 8,000 some odd word lines and 8,000 some odd digit lines. The spacing between the arrays due to the row decode is 93 micrometers and 45 micrometers due to the sense amps. So it's at 93 micro. This is the dimension that we're changing by changing the type of row decode that we have in there. We can make it smaller if it's a global. We can make it huge if it's local, and we can make it somewhere in between if it's hierarchical. That's the only number we really have to play with. You couldn't do this with camera chips. That's what I designed. That's one thing I like about cameras. You have to make the whole pixel array. You can't put the row decoders and the sun amps in between there. We'll get to that later at some point. Okay, so I've got a local row decode with folded, and with the local row decode, the row decode strips are 93 micrometers with the folded. Oh my gosh, this is huge. 40.6 million micrometers squared. Folded local, 40.6 mega. Remember, part of the issue is here too, with the folded architecture, our mbit size went up to 8F squared. Can I beat that? Remember, but remember, this was our biggest one here. So maybe if I go to a global or a hierarchical, I'll be able to get those down to where I want them to be. Yeah, there's engineers who do stuff like this all the time. There's engineers that just do budget calculations all the time, trying to figure out how they can get the best cost out of this. Okay, I go to the global decode. Where is my, whatchamacallit? Number I'm looking for was right there, height of local decode strips. The height of the global decode strips is 200 micrometers. And the local was 93, but I have fewer of them. And so it comes out, I'm back down to 32.6 mega, folded global. Folded global, 32.6, folded global. This is so much easier to do on the board. Okay. I'm in the same ballpark. I could probably do open local and maybe squeeze it down a little bit more, but it's got an SNR problem that I really don't like. We go to folded hierarchical. The global decode strips are, wait. Now I'm folded global decode. This is hierarchical. I have fewer of the hierarchical strips. The width, the height of them is a little bit smaller, about the same number, but still I'm multiplying this by a large number, the number of rows I have. It's down to 34.1. Folded hierarchical. Folded hierarchical 34.1. It's in the ballpark. I have improved the SNR, which means I can make the sense amp smaller. So there's yet another trade-off that isn't even done in this. Okay.
Not the size quite yet.
It's complicated. When we did, I can kind of tell you how this process works. I was at Motorola, and we had, when we were figuring out what frequencies we wanted to operate our phone at, we were given the band of frequencies by the FCC and the equivalent of the FCC in whatever country we're building the phone for. So we're stuck with that. But we could choose, we'd have to go down to these intermediate frequencies for, I don't know if you guys know how a heterodyne receiver works, but you start out at like 900 and then you drop it down to 45 megahertz and then you drop it down to baseband. So there's an enemy, yeah, okay, I'm just talking gibberish now. Okay, so there's these, you have choices on what intermediate frequencies you can use. And based on the IF, the intermediate frequency, you would get spurs at different frequencies. So the guy who is like the senior principal staff engineer had this spreadsheet, and he would be the guy plugging in the numbers into the spreadsheet to say, okay, what is the optimal IF based upon and there's only certain frequencies you can buy components for. If I use the 45 megahertz, will it work? If I use the 38 megahertz, will it work? Will I have spurs? Will I have spurs in my signal band? Will the spurs in my transmission signal band crosstalk with my spurs in my receiver signal band? Just a mind-boggling array of decisions. So he basically, I've seen him do this. He had a spreadsheet that he wrote for this. And he'd plug in the numbers and he'd come up with, oh no, this is bad. And then he would just magically make the pronouncement to everyone on the floor, thou shalt use 45 megahertz. And no other. And then suddenly we actually discovered a new spur that ended up like right in the middle of the receive band that upset the heck out of people. And
What's a spur?
a spur. When you take signals, okay, and you mix them together, you're multiplying a signal at one frequency with a signal at another frequency. What you get out is all the sum and difference frequencies of those two signals. So let's say you're at 1 gigahertz and 45 megahertz. You would get A times 1 gigahertz plus or minus B times 45 megahertz, and A and B can be any integer number, and it will actually produce spurs at all those frequencies. Normally you just filter them out.
Similar to like some of the 348 stuff.
Yeah, it is like 348 stuff.
Yeah, 348 stuff. Willie?
There's no one else, is there?
What?
At 348.
Well,
No, Alpha.
Alpha's not teaching it anymore. Willie's teaching it.
Severn House.
I don't think Alexander's teaching it either.
Professor Willie is the only one.
But I think Ofka wants to just do research right now, and Severnhouse is busy with capstone.
Yeah.
It's interesting.
Okay, I'm sorry. Shh, I could actually teach 348, but I'm not going to. I'm just going to claim it's math. I don't need another class to teach. Okay.
Your semester to de-stress from last semester.
Yeah.
And I'm at a full schedule. I have ways to. I have a cunning plan to fix this. I'm not going to tell you guys. I'll tell you later. Okay. Folded hierarchical row decode. Did we get that one in there? Folded hierarchical row decode. Yeah, that's this one right here. This is a line. Okay. So we go through. So this is basically, and the reason why I stopped for that whole signal mixing nonsense is at Micron, I'm sure there is a guy somewhere who has the spreadsheet that has all this stuff in there that just goes through and does these calculations and tells everybody, you will use folded hierarchical design for this chip. It is. It's great being that guy too, because you do. Okay, I'm sorry, again, comments from the classroom. Fallon is working at Gore now.
Is she that person?
Well, no, but they think she's amazing because she can program in Excel. And some fancy languages like C, but no one knows how to use those.
Ooh, C.
Okay. The real world is much more archaic than you can imagine. Okay, so the bi-level fixes the problem of the SNR problem that we had with the open. Good SNR. But it does it with the smaller cell size. So I should be able to get both the high SNR with this one, and I can get a smaller array size One thing that's going to increase the array size are these twisted digit lines, and we'll look at those in a little more detail today. Remember, we want to twist the line so I get the same noise on the DL signal as I do in the DL not signal going into the sense amp. I need another metal layer. Metal layers are relatively cheap now, but it will add to the cost of the processing. All these things have to be taken into account on somebody's spreadsheet.
Spreadsheet somewhere.
There's the spreadsheet somewhere. It gets handed off to the next. To the next. It's in Microsoft Excel 93. So I've got the row decoders coming in here. I have the digit lines and the digit line knots. They cross in this vertical twist. And we're going to look at that in a little bit more detail too as we go through these architectures. Now, I hate this picture. I really do. Every time I see this one, it makes me croak because let's look at this. If I take digit line top that's in metal and I cross it over to digit and make it digit line bottom, and then I take digit line bottom and I cross it over and make it digit line top, what happens here? I've just shorted the two of them together. It doesn't work. We can't cross them without putting another layer of metal in. Yeah, and which the guy with the spreadsheet's got to figure out what's the trade-off is. Okay, I can do this alternating twist where I twist one set of digit lines on, and then I don't twist the next set, and then I twist that one, and I twist the other set every other one. So this is called a standard triple twist. The non-twisting lines give you the extra room you need to do the vertical twist on the others. And I haven't convinced you yet that this is possible. 20, 21. It does come up in here. Oh, yeah. This is how you do it. I have to put a third layer of metal in there. So here's my digit line coming in. It goes through a via down to the intermediate layer and then goes through a short trace there, the minimum size trace you can get, into a via to the third layer, and then comes across, and no shorting. And then it has to come back up again.
Goes elsewhere.
And goes elsewhere.
So that's how the twisting is actually done by the weird diagram.
You're not actually twisting the lines.
Yeah, it's just
It's done by going from layer to layer. Vias, the magic of vias. And then let's give this a different color. The digit line knot is starting out on the bottom layer, and it stays there, but it has to be separated from the other one. And then it's going to go up through vias to the top layer. I need an extra layer of metal to do this. And believe it or not, there are more complicated schemes to do this, depending upon how many twists you want to do.
So I'm assuming that you have to kind of add another layer per twist that you do.
Yeah.
Okay. That's not the worst thing in the world, but you're right, the other diagram does kind of hurt.
Yes, it does. Back when I was doing IC design, getting a process with 4 metal layers was seriously amazing. Now they've got them with 12. Again, you're going to have yield issues because you've got all those extra layers. Every time you put another metal layer down, you're going to blow something out below it. So there's some yield issues with it, but on top of that, it's going to be more expensive. It's going to take more time to process. Every time you put one layer down, think of it as being a week in the machine.
Like last, look at this third diagram down there, because that just okay, yeah.
Yeah, okay.
It was twisting in a way that my eyes didn't like.
Yes, they're twisted. Okay. So my embed cell is now 6F. This is bi-level plaid. Oh, I do not like the red on the green.
Christmas.
No, it's like it's contrast. They're opposite colors. They glitter to me. Okay.
You have a little bit of red green color on it?
No, but I see things differently than other people do. I can see I can see higher frequencies than I should be able to. I had a lot of trouble with computers back in the day when they had the until they got above a 60 hertz refresh rate on the CRTs, I could see them blinking and no one else could. And it would just completely wear me out by the end of the day if I was sitting in front of a computer terminal.
Yeah. Yeah.
Yeah. And people tell me that's impossible. So some people told me it was impossible, but no, I can't.
My eyes can't focus on neon orange.
Yeah. And then weird things like this. This just is just like glittering because it's red on green. So I've got here for my embed size, I've got a half a contact. I'm still going to share the contact with the adjacent cell. I've got the word line for this one. This is the transistor right here. The metal layer is going through for the digit line. This is the word line. And so this is the drain of the transistor. This is the source of the transistor. And the source is going through to the capacitor, just like in that embed cell you designed for the project. Some of you have done. For the spacing, I have the space of, I've got one feature space right there for the active area, and I've got a half a space on either side of it. So I've got 2F in that direction. And this is how it looks when I put the whole thing together. Shared digit line contact, two capacitors and 2 transistors share that digit line contact. And the active area is actually this little thingy right here. That's the source of the transistor that gets tied directly to the capacitor, which is the circle underneath there. You get to read one of these later on. That's about it. We're not doing layout. We're looking at layouts. Okay, by level, I want to figure out what the digit line length is. Remember, my current was limited to 200 milliamps, and this should be in milliamps. And so I am looking at a 256 digit line length, which I think is about the same as everything else we've done. I should get a chart going for that too. Okay. I need the extra metal layer. There are rules. If you ever do layout, do not violate these rules. Our standard cells, our AND gates and our NAND gates would all be routed in poly and metal 1. The contacts among the gates would be routed in metal 2 and metal 3. Every company is going to have their own set of rules. Pay attention to those if you're doing routing. Metal 1 you usually do for the lower level stuff. In a memory cell, in a memory array, that's going to be the lower level digit lines and some local routing. You do the lower level stuff in metal 1. The upper level digit lines are going into metal 2. Column select routing through the sense amps are in metal 2. You'll have a set of rules wherever you're at. And don't violate these because you'll upset the heck out of people. Trust me. I had to do all the routing for the microprocessor.
Make sure they're ground.
Where's Hancock? Clock trees and all that stuff would be Bruce Hancock's job. You guys know about clock trees, don't you?
You mentioned it once at some point.
Okay. You have a clock, master clock coming in. It's got to get routed to I don't have no idea. It's got to get routed to every flip-flop in your device. And you want the relative delay, you want the edge to be exactly the same at every flip-flop. So one flip-flop doesn't trigger a little bit before the others. So you've got to create something called a clock tree. That master clock coming in can maybe only drive 10 clocks, but it's got to drive thousands. So the first thing you do is you take the clock and you divide it up and you buffer it to 10 subclock drivers. And then you take each one of those and buffer them to 10 subclock drivers. And you keep doing this until you have enough drivers that are the same.
So it's exactly what it sounds like, a clock tree.
It is a tree. Now the trick is you have to keep the line lengths between the buffer, the last stage buffer, and the last stage buffer and the previous stage buffer. You got to keep the line lengths all the same to keep the delays the same. So you're going to put like a clock buffer somewhere down here that for this part of the array, another clock buffer up here, and you got to keep the line lengths between all of the stages the same.
Well, it doesn't sound bad, it just sounds irritating.
It was a job for Bruce Hancock.
Yeah.
He just loved doing stuff like that.
Not horrible, but sounds irritating.
It's a little tedious. Yeah. Okay. So just, yeah, pay attention to the routing rules if you're doing routing. The word line pitch, I have 4 word unfolded, 2 word lines per 3 features. Per 3 features, 4 word lines per 4. I've got an easier layout for the local row decode with open and bi-level. The odd and even word lines are driven from the same block, so that is what is going to relax it a little bit. Where am I going with this? Bi-level, Sun Samson, local row decode, right? And with the bi-level, the additional thing is most of the stuff is pretty standard. We put the sense amps on each side of the array block. So I've got every other row kind of going through there. I'm going to put a local row decode on one side of the block. I can do the local because of the extra double word line pitch, but I still need that extra room for the twist areas. All of these things get taken into account. I'm sure you're not going to, okay. Remember any of this except for I told you that somebody calculates this with an Excel spreadsheet. Thank goodness. You don't have to do everything. You do your little piece of it, and then you make it work with other people's little pieces of it. So I can kind of squash these together, these subarrays, and I can put the sense amps here, and I put the row decode is shared between 2 blocks. So that is one way of squashing it together. So, but when I take all this into account, I get my local strips are narrower. They were like 200 micrometers before. So there are a lot less space in there. With the bi-level, and this is local, I'm at 28.7. Bi-level local. Bi-level local 20. This looks amazing. I can score, it's got a smaller, you know, this is a 6F squared. This is an 8F squared. And this is a 6F squared. Okay, so that really helped. Squunching down the size of the array and having that relaxed word line pitch.
So bi-level is just generally better than open.
Yeah, there's a drawback. Bi-level is the best thing we've gotten so far. I'm sure they've got other stuff now too. If I go to a global decode, I'm down to 24.3. Oh, that looks so beautiful. Why don't we just all use bi-level?
I'm waiting for the caveat.
You're waiting for the, we're waiting for the engineering trade-off. I'm almost done. Oh, good. Go to hierarchical. I'm at 24.9. Wow, I'm actually, even with all the babbling, I'm not. 24.9 mega. Okay, so this looks amazing. Why don't I just always use bi-level? Here's the issue. How many metal layers do I need? I need one more metal layer. It's going to cost me a little bit more. So I got to look at the trade-off here.
Is that it?
Well, no, no, oh, no, okay, so if I make the arrays, if I make the subarrays smaller, my chip size is going to be smaller. So it's going to cost a smaller percentage of the whole die cost. This is going to be a smaller percentage of the die cost because it's smaller. But the die cost is going to be bigger because I've got an extra metal layer. So you've got to do the calculation to figure out what the cost per die is, and then figure out which one you want to go with. The actual size of the actual size of the memory chip is going to be nowhere near as big as the size of the package. You could always make the actual die bigger. It's how much does it cost to put it in there.
Okay, so
More expensive processes. This is four metals is going to be more dollars per micrometer squared, but I have fewer micrometers squared. Is it? And then that you
yeah, so at that point you were literally just like crunching numbers to find out which is generally more cost effective.
Right.
And at the end of the day, that's what we're looking at for a product.
Right.
It's the most cost effective.
Yeah. And this is the kind of calculation they're not going to trust a pup engineer with. Yeah, they're going to give it to somebody who's going to tell you you're going to use bi-level plaid and you're going to use this number of metals. Yeah, spreadsheet man. The one who's going to take the responsibility for it because he's been there 20 years. Spreadsheet man. We all become spreadsheet man.
Spreadsheet wizard.
Do people generally use the open architecture nowadays? Because isn't the signal to noise ratio?
Yeah, I think the open architecture is pretty much gone.
Okay.
Yeah.
So open's gone, and it's now just between folded and bi-level.
Well, there's more than, there's probably, they've got more stuff than that now too, that they're just not sharing with the rest of the world. The part of the problem with keeping up to date on this stuff is a lot of the little things that Micron figures out that makes their chips a little bit cheaper. Memories is a really cutthroat business. If as soon as Micron gets a 4 terabyte drive that is $2 cheaper than Samsung's terabyte drive, everybody's just going to go buy Microns. There's just no.
So then
It's all cost, and then Samsung comes up with one that's like $3 cheaper, and it's a commodity. And so if you have these little tiny trade secrets that give you an edge over the competition, you don't publish them and you don't share them.
That's where the NDAs come in.
Right. When I went to Micron, I don't know if we'll be able to go this year or not. We'll see how things are in April, May. We went to Micron 2 years ago. We all had to sign non-disclosure agreements before they'd let us in. And then, but once we did that, it was like you can talk freely to them. And here's a group of young engineers coming in there, and they're allowed to talk freely to people for the first time. So they just babbled endlessly. They would tell us everything. We even found out they were working, what the Optane drive was. We found out all kinds of little things that, and they showed us that they were able to show us stuff freely. But if you had gone out, the problem would be is somebody had gone out and went to work for Samsung 3 months later, they would probably be a little upset.
It's on the NDA, so
Yeah.
you can't, it's not like they can really.
They can enforce that.
Well, no, I'm saying that.
Yeah.
It's not like that the new pub managers can really go tell Samsung that they.
Yeah, but sometimes things just flip out.
Yeah, because the NDAs get enforced and things come out, but then there are consequences.
Right. And the way they kind of get around some of that, just cutthroat commodity pricing is Samsung, not Samsung, Micron has a whole building called technology development, and they work with big customers. They work with Microsoft and Oracle and all these people doing server farms, and they custom build chips specifically for their application. And then that way it's kind of like, they're kind of like locked into that custom chip. And those chips may change every 12 months or so, but yeah. Okay, we're getting there. This is without all the decimal places. What is that? Okay, another thing that's kind of in here too is the efficiency. So this is important too. This is telling you how much of what percentage of your micrometer squared are actually available for memory in bits. And you can see here, and this is including the fact that I've got to put the global decode block someplace else. It's still going to be on the chip. So you can see the best efficiency here is global bi-level with 4 metal layers. But does that outweigh the increased costs of the 4 metal layers? And I don't know, I don't have the numbers for that.
Digital folded global is pretty good too.
It's pretty close.
Yeah.
This might be because of the cost of the additional metal layer in both time and processing cost. This might be a more
efficient,
cost-effective decision. Yeah, that's the word I'm looking for. Which one's which?
Oh no.
There'll be a quiz on this at the end. We didn't know that.
Can we actually play this game?
You can play this game now. Which one of these things is not like the other?
What was it? The C fold. No, C is open. Right? I think A is.
C is open. Yes.
I think, is it?
A's gotta be folded.
Yeah, A has to be folded, I think. And then that would mean B is bi-level.
Yeah, it's.
You can see the sunset going 5 levels, 1 arrow movement.
Yeah.
Yeah.
Yeah, so are we right about that?
B is folded.
Oh, B is folded? Okay, so then A is bi-level then.
A is bi-level.
Okay.
What's the date to drop this class? If I got that wrong.
Don't worry about that. That will never be on an exam. I have trouble with this one still. I looked at my notes to make sure I was right. The difference between bi-level and folded. Okay, folded is going to take. Okay, so this is taking it from adjacent. The sense amp is going from adjacent digit lines. On the bi-level. Wow, that is just weird. This is just wrong.
That's wrong.
The bi-level is showing both sides of the sense amp being connected to the same line.
Oh, then it runs into the issue of that painful diagram.
Yeah.
being shorted.
Oh, no. Okay, so there's a difference. It says right here, there's a top digit line and a bottom digit line running through all of these. That's going to get twisted. And it's the top digit line and bottom digit line that tells you it is bi-level.
Oh boy, I can't wait for tri-level.
Tri-level. Oh yeah, there is a logical conclusion to this twisting. There's a whole set of slides. There's like 3 or 4 slides.
Is that what happens next time?
I haven't looked that far ahead. What's next time or not? Chapter 4 is, I don't know what chapter 4 is. I don't have it in my slideshow. Oh, I do. I have it here.
We're in chapter 5.
No, the slide numbers correspond to chapter numbers. We're in chapter 3. Chapter 4 is global circuitry. So the global circuitry is going to be the decoders and the drivers that are driving the actual array. So we need some peripheral circuitry for that. And it really, in modern memories, there's also an entire microprocessor on the memory to control things like, I've got a bad row and column here. I've got a bad row here. I need to map that address into a new address. Not only that, they found out that hackers really love it when if the physical address of the bits equals the memory address of the bits, so they scramble them, and they got a whole algorithm for how they scramble them. So you put in row and you put in a row address, and it's not going to be. If you put in row address 1, it's not going to be the second row in the array.
I'd like hell to try to understand the schematic for it.
They showed me a map of it based upon, it's like a color gradient based upon increasing numbers, and it's all over the place. They're scrambling. They're scrambling like blocks of columns too, within a row.
Necessary.
It is.
You have good stuff.
Yeah, I found another one in there, and I just copied it. It's okay.
It's a really good stuff.
It's a really good study.
We
Okay.
got 15 minutes.
We got 15 minutes left. If anybody has any questions about the project, I will take those. If not, you're free to go. Only people I'm missing are Matthew, Shujian, and Yuhao, and they usually watch later.
And Matt might be
I don't know where Matt is.
non-existent.
Yeah, if you know Matt, if you're friends with them, send them an email or something. Tell me so I'm multi classes.
The only connection I have with Matt is on LinkedIn.
Okay.
Is that it?
Yes, you can.
Okay.
I do it all the time. I messaged Heather this morning.
Yeah,
And I annoy people forever.
And LinkedIn is basically just professional Facebook.
No, not really. The way I use it is I don't go to the news feed whatsoever because it's just pointless. I use it to message people if I don't have their email address, or if they move. A lot of times people change companies, especially early in their career. So it's the easiest way of keeping track of alumni. Yeah.
Julie, you have about to have a list somewhere of all the people that were in IEEE previously.
No.
Okay. Maybe
You could always join the NAU IEEE Facebook group.
I'm in it, yeah.
Okay,
That's probably a good way of doing it.
I look through there.
Yeah, because apparently Hunter needs a list of all previous members for whatever reason.
Okay,
So,
that would be a good place to start.
yeah, I'll probably start putting a list together. to do
Okay.
that.
Okay. I can stop recording now. Nobody's asking me questions. Nobody's. Okay, good.